Let me just use this tool for some of the simpler things first. And I think that some of the things where we can get a quick mileage, is that the right term? Out of it is redraiving these two formulas that you guys have seen on Tuesday. So with the time dilation, this is what I remember. So if you have some clock that's measuring its own time, proper time, then, and its clock is zipping by you, and you measure the ticking of the clock with your own clock, then the time you measure is gamma times the proper time. And with a ruler, if you have some ruler of its own length, proper length, measured in its own reference frame, then what we derived last time is as the ruler is zipping by you, the length you measure is contracted, so it's shorter. So it's not proper length times gamma, it's proper length, it's proper length divided by gamma. That sounds familiar, yes? We derived these two last time from the two postulates of special relativity. Mostly the second postulate, that speed of light is constant at c. And what we are going to do now is we are going to use this transformation to rederive these two formulas. And because I haven't derived this transformation, I'm just giving it to you. This is something I've memorized. And I want to give you some indication that this is actually correct. And I'm not sure if I can ever actually derive it from first principles. So I'm doing the other thing. I'm using it to derive an expression that if we can get the same thing, then we have some confidence that the thing it came from is probably right. Yeah, this isn't logic class, it's a science class. I guess this is enough of the pieces to derive the time dilation. So let me try to do that. So, with time dilation, this is what you're imagining. I have the cart, now I have a clock on it, and it's going to be moving. So as it goes, so along this ct prime axis, so x prime is equal to 0, but you can count off how many seconds there are. So, counting from here, let's say 1 second, 2 seconds, too many dots, 3 seconds, 4 seconds, and so on. Right? It's counting off seconds that way. So let's say let's define two events. By the way, this is a bit of a term that I should probably define. When someone says event in the context of special relativity, what we mean is we are trying to define a space-time coordinate. Space-time coordinate, like t, x, y, z. Okay? We call it event rather than just coordinate or point, because when you say coordinate or point, a lot of people just think of this, spatial coordinate. When we say event, we are being more clear that we are including the specific time. So this moment here, it can be an event. Like it can be a real event of this crossing 0. Good? So let me call this event A. And let me call a later event, call this, let's say, moment at which it measures the time equals 4 seconds. Let me call this event B. Good? We can describe the coordinates for both of these events. A is kind of boring. The event coordinates for A is simply, how do I write this in a way that's not all that confusing? Let me do it this way. So I'm going to skip y and z. I'm not doing anything with y and z. Let me just skip writing those. At A, the time is equal to 0, x is equal to 0. So time is 0, x is equal to 0. What about in the primed coordinates? T prime is also equal to 0, right? That's how I'm defining my coordinate system. So T prime is equal to 0. What about x prime? Probably 0, right? Okay, so all right, so good. So this is my, A is just my origin event. So this lets me, so I want to measure an interval, some kind of difference between events. Putting one of the end of the interval at the origin means I can just deal with the coordinate of this, and that will actually mean the difference. So B is the more interesting point. I can describe point B by its x. So let me call this here. Let me erase the stationary tape since I'm not doing anything with it. The boring tape is gone. So I can choose to describe this point B by my x prime. So let me call that xb. Oh, sorry, not prime, just the xb coordinate. And the time, tb coordinate. I can do that. Or I can describe B by the primed coordinate. So this would be where, some kind of t prime b. And do I know what its x prime coordinate is?
It should be orthogonal with timeline prime.
No. I'm just asking for at this event b. Do you guys know what the x prime value of the x prime coordinate is? We just went over it.
0.
Yeah, 0, because it's along the axis, t prime axis, right? Yeah. So x prime is, I could x prime b is equal to 0. Okay? Knowing this will make things a little bit easier as we do the next calculation. So this is what we are going to do. This is the general expression. Let me plug in the, so here I guess it's actually the value of the primed coordinate that we know. And we are trying to figure out the value of the unprimed coordinate. And from our description of proper time earlier, it's this. That's actually my proper time tau for this clock that's sitting on top of the, that's going to be moving from my reference frame. Okay? So let me plug in this into Lorentz transformation. And my goal really is to try to solve for this time, because that's going to let me relate the time that I measure in my own reference frame with the time that's being measured by the moving clock. Good? Okay, so let me write it down. So I'll just copy. So I'm going to start just ignoring the last two because that doesn't do anything. I'm getting tired of writing those. So let me just work with these two. So I have Ct prime, so Tb prime is equal to gamma Ctb minus beta xb, neither of which I know. And I have x prime, I know that one, that's 0, is equal to gamma x, I don't know what that is. Let me just write it down as xb minus beta Ctb. This is a system of two equations. So I'm hoping I only have two unknowns. If that's the case, I can do the algebra, solve it. Good? Okay, so Tb prime, that's the one that I presumably know. I presumably know how many, let's say I know proper time. Let's say I know proper time. Then I don't know the time being measured in my reference frame or the position being measured in my reference frame. Any other unknowns? Okay, if you're assuming that the velocity is constant, some value we know, then beta is known. And this is something I want you to get used to, by the way. Beta and gamma actually specify one and the same thing. Because of this relationship here, whenever you know beta, you actually know gamma. Whenever you know gamma, you actually know beta. You can actually invert this. The inverse of this is beta is equal to, I think it's a square root of 1 minus 1 over gamma squared or something. Maybe. That doesn't sound right. Yeah, I think that's right. Close enough. I'll double check when I actually need it. So yeah, two equations, two unknowns, we can solve it. And I guess looking at it, I don't really care for xb. So let me eliminate xb and just solve for time that way. So I guess it's easier to solve for xb here. I can just cancel out gamma. It's 0 on this side. So dividing by gamma, I get rid of gamma. So xb is equal to beta c TB. Does this surprise anyone? Position here is equal to velocity, beta c, times time. Like, if you were guessing, you would have guessed that, right? Yeah, and that is correct. I mean, from the Lorentz transformation. It's not giving you anything that's contradictory to your intuition yet. Plug this in here, then this is what you end up with. CTB prime is equal to gamma CTB minus beta squared C TB. All right, let me cancel. I think I have C factor on every single term, right? So let me cancel that out. C is gone. I can factor out TB here, so let me do that. I have gamma times 1 minus beta squared times TB. Now, only if I could simplify this further. Can I? What is gamma? This, right? Or 1 minus beta squared raised to power of minus 1/2. Well, I have this, 1 minus beta squared raised to power of 1. So I can actually combine these two to get me 1 minus beta squared raised to power of 1/2. Or I guess the gamma is the expression we actually prefer most of the time. So this is equal to 1 over gamma. Okay. So with all that algebra, this is what we end up with. So TB prime is equal to TB over gamma. Hey, is gamma on the wrong side? Oh, we are okay, because it's not the TB that's the proper time. It's this that's the proper time, right? So rearranging things so that I have proper time on the correct side. What we have is TB, which is the time we are measuring in the lab frame. We are not measuring the proper time for this clock because the clock is moving from my frame. So TB, time I measure in lab frame, is equal to gamma times the proper time, or I guess TB prime. This is the proper time tau. Good? That's what we were expecting to see. That's what we get.